Hello class, welcome to lesson 6 of the calculus series. We're looking at limits at infinity. So you may recall in the last class, or in the last lesson, we looked at infinite limits. So now we're going to look at what happens for limits as we approach infinity. So in order to demonstrate limits at infinity, we're going to talk about the horizontal asymptote. You may recall that in the previous lesson, we looked at infinite limits and we looked at behavior of vertical asymptotes. So now we're going to turn to the behavior for horizontal asymptotes. So for this lesson, we're interested in determining the end behavior of the function. So suppose we have a function f of x defined by 5x squared over 2x squared plus 3. We want to determine the end behavior of the function. In other words, how does the function behave as it approaches infinity on the left side as well as the right side? So as it approaches negative infinity as well as approaches positive infinity. So end behavior is described as how the function behaves as x increases or decreases without bounds. In other words, infinitely. So let's look at a table where we examine the behavior of this function as x becomes really negative, so approaching negative infinity, and as x increases without bound, that is positive infinity. So we got some pretty large values. We got x going from 0 to 1 to 10 to 100, and then on the left side of the number line, -1, -10, -100. So we're looking at x increasing and decreasing without bounds and examine how the function behaves. So first, if we calculate those values and we plug in, for example, x equals -100 into the function, x equals -10, so on and so forth, we get the following values. And so you start seeing that as x decreases without bound, it's approaching some value, and it looks like it's approaching 2.5. It goes from 1 to 2.46 to 2.49. So it looks like it's approaching 2.5. As x approaches positive infinity, you see it's doing the same pattern. It's approaching 2.5. So if we continue this pattern, we can see that the values are approached 2.5. So this means that as x decreases without bound, that is, gets more and more negative, the limit as x approaches negative infinity is 2.5. And then as x increases without bounds, which is positive infinity, the function tends to approach the value 2.5. So we determine the end behavior of this function by looking at a few examples of how it behaves as we get larger and larger or smaller in the negative. These limits are known as limits at infinity, and this is the topic of our lesson today. So if we were to graph the function f of x, we can see that as x approaches positive infinity, the function starts to approach this value of 2.5. As x approaches negative infinity, the function approaches that same exact value of 2.5. And this is our horizontal asymptote that we mentioned earlier. So this here has to be our horizontal asymptote. So like I mentioned earlier, the value to y equals 2.5 is the limit of the function at infinity and is known as the horizontal asymptote. So let's go ahead and define what the horizontal asymptote is. So it's the line y equals L, where L is a number, L is a constant. And so y equals L is a horizontal asymptote as long as when we take the limit at infinity, negative or positive infinity, we get the value L. And that's what is referred to as a horizontal asymptote. So as long as the limit at infinity is, or negative infinity is a value, then that value is taken to be the horizontal asymptote. All right, so here's the theorem for limit at infinity. Suppose n is an element of the positive rational numbers. So you see this plus here means we're dealing with rational numbers, namely, numbers that can be written in the form a over b, such as fractions, etc. But they have to be positive rational numbers here. And suppose that c is an element of the real numbers, the set of real numbers. Then the limit as x approaches negative infinity of c over x to the n is equal to 0, and the same limit, but evaluated as x approaches positive infinity, is 0. As long as x to the n is defined for x being negative or x being positive. So essentially what it's saying is that this power here it can be any positive rational number. So it could be a fractional exponent. It can be a whole number exponent, right? It's just saying that it has to be a positive number, and there's a reason for that. And c is just a constant. C can be any real number. So for example, if I have the value 1 over x to the 5th power, well, you can see 5 is a rational number and is a positive number. And so if I take the limit as x approaches infinity, well then what happens to that value as x gets bigger and bigger? Well, if I plug in 1 for x, I get 1 over 1 to the 5th. If I plug in 2 for x, then I get 1 over 2 to the 5th, which is, 1 over 32. If I plug in 3 for x, I get 1 over 3 to the 5th, and so on and so forth. So as x gets bigger and bigger, what happens to this fraction? Well, this fraction gets smaller and smaller. And it gets so small that it approaches 0. So you can see that this fraction is getting smaller and smaller. And of course, the limit is going to be when it approaches 0. All right, and this works for positive and negative infinity. So if we plugged in -1, -2, -3, so on and so forth, you get the same result. All right, so that is what that is referring to. So if we erase this and we look at an example, so if we look at, for example, 10 minus 3 over x to the 4th power, we take the limit at -infinity. Well, we can split that up into two separate limits. We know that the limit of the limit at infinity for 10 is just going to be 10, because 10 is a constant. And then the limit at -infinity for 3 over x to the 4th is 0. So this goes to 0, as we mentioned earlier, and therefore we get the value of 10. All right, so there are under the indeterminate forms that I want you to be aware. So 0 over 0 was an indeterminate form that we noticed in the previous lesson, in one of the previous lessons. But there are other indeterminate forms. Remember that if you got an indeterminate form, that indicates that we might have to use a technique to tease out the value of the limit. And I put that in quotes, just to figure out, because 0 over 0, indeterminate means that, there's no, we can't determine the value of that form. And so we have to use techniques to figure out what the value of the limit actually is. And here are some other indeterminate forms. So 0 over 0 is one of them, as mentioned earlier. We also have the indeterminate form infinity over infinity. So if we have a form like that, we cannot determine the value of that. Notice that we said that if we had a constant over infinity, that is 0. So a constant over infinity is actually not indeterminate, as mentioned in the previous example, that if we have a constant over x to a power, right, a positive power, and we take the limit as x approaches infinity, well, if you plug an infinity into there, infinity to a positive power is infinity, so we get c over infinity, which is just 0. Okay, so we know that a constant over infinity is not indeterminate. It actually is a value that we can determine. So, but infinity over infinity is definitely indeterminate, whether it's positive or negative infinity. The next indeterminate form is 0 times infinity. I know it looks very odd, but 0 times infinity is an indeterminate form. 0 times positive or negative infinity. And if we have infinity minus infinity, that's also an indeterminate form. We cannot say it's 0 or any other value, because some infinities tend to grow at different rates than others. And you'll see that when you look at some other functions examples, but that's indeterminate. And we have 0 to the 0 power, as that's also indeterminate. 1 to the infinity is indeterminate. And the last one is infinity to the 0 power. So in this lesson, we'll be focusing on indeterminate forms, infinity over infinity. And we're going to see those in this lesson, and we're going to show you how to deal with those. In future lessons, we'll look at other indeterminate forms. So when you encounter infinity over infinity, you need to divide the numerator and denominator by the highest power of the variable in the denominator. So let's give you an example of this. If we have the rational function 3x over 5x squared minus 8, well, notice that the highest power of the denominator is 2, x to the second power. So we divide by x to the second power in the numerator and denominator. Then you notice here we divide by x to the second power in the numerator and denominator. We notice that the x squareds cancel here in the denominator, leaving us with 5. We got 8 over x to the second power. That should be an x raised to the second power, by the way. And then one of these x's cancels, leaving us with this fraction here. This is a complex fraction. So this is how you deal with infinity over infinity. And we'll show you what happens as we take a limit at infinity of this. It's actually going to fix our problem. But this is the technique. So let's use the technique in order to find this limit here. So notice first that if I do a direct substitution, and again, that's a typo right there. There should be a T there for substitution. So if we do a direct substitution, notice that we can take the limit of the numerator and denominator separately. And if we input infinity in for x, well, we know that infinity to the second power is infinity. 5 times infinity is infinity, and infinity minus a constant is infinity. So we got infinity in the numerator, and infinity to the second power is infinity. So we got infinity over infinity, which we determined is, well, which we mentioned was an indeterminate form. So therefore, we have to use a technique. So we're going to take the highest power in the denominator and divide the numerator and denominator by that, okay? So the highest power in the denominator is x to the second power, so we're dividing numerator and denominator by that. So then when we do that, notice that the x squareds cancel, leaving us with 1 in the denominator, so we can ignore that. The x squareds cancel here as well, leaving us with 5. And we got this expression here, 5 minus 2 over x squared left over. Now we can take the limit as x approaches infinity, and notice I can take it separately. The limit of 5 is just 5, but then if I plug an infinity into x here, that gives you infinity. 2 over infinity is a constant. Okay, remember a constant divided by infinity is 0. So we get 5 minus 0 is 5. So therefore, we avoided the indeterminate limit problem here. All right, so therefore, we have a horizontal asymptote at y equals 5 to the right. And we mentioned that it is to the right because we're doing the limit at positive infinity. So really, we can only establish that there's a horizontal asymptote on the right side. We need to actually determine it on the left side as well if we want to figure it out. Sometimes the horizontal asymptotes vary on the left and right sides. So if we take the limit as x approaches negative infinity, that will establish a horizontal asymptote on the left. But notice that you'll get the same answer. So I leave it to you as an exercise to determine the limit at negative infinity, but it's very similar to the steps here. In fact, it's the exact same, except you use negative infinity here and here. All right, so you're going to get 5 as the horizontal asymptote to the left. All right, so let's look at another example. So for this, we want to do the limit at negative infinity. If we do a direct substitution for this, we notice that we get infinity over infinity. If I plug in infinity in or negative infinity, so remember negative infinity to the second power is positive infinity because, you know, a negative number raised to the second power is positive. So we actually end up getting positive infinity in the numerator and denominator. All right, so we went ahead and corrected that little typo there. So we got infinity over infinity. So as mentioned, if we get this indeterminate form, we want to go ahead and divide by the highest power of the denominator, which is x squared. So if we do that to the numerator and denominator, notice that on the we continue to simplify this. X squared over x squared is 1. And then we get this x and x squared, one of those cancel. And then we get this expression. This is a complex fraction here. We got a fraction over a fraction, or set of fractions. Next we're going to take the limit at negative infinity. So if we plug in negative infinity into x, well, notice that we have a constant over infinity, which that turns into 0. We have we have a negative infinity squared, but a negative squared is a positive, so that leaves us with 1 over infinity. So therefore, you know, it's going to be this infinity turns positive. And then we got this negative infinity, which turns positive over here. In any case, a constant over infinity is 0. So this infinity, these 1 over infinities actually go away. So we have 0 minus 0 on the top and 1 plus 0 on the bottom. So overall, the limit is 0. So therefore, we have a horizontal asymptote at y equals 0 to the left. And if we do the limit at infinity, where we do positive infinity, we're going to get a similar result. We're going to get 0 for the horizontal asymptote. So I leave it to you as an exercise. It's the same steps to simplify this in the same manner. All right, so let's look at yet another example. Notice that the examples are very similar for this. The only main difference is if you look at the previous example, example 2, this is to 2x to the first power. If you look at the example before that, it was it was a different power as well. This one is 2x to the second power. So let's go ahead and evaluate, do a direct substitution. When we do that, we get infinity over infinity. So we're going to divide by the highest power of the denominator, which is x squared. So doing so leads us to this. So we got this complex fraction. We're going to do a little simplification. The x squareds cancel. So then if we plug in the limit as x approaches negative infinity, we plug in negative infinity in for x. Notice that this negative infinity turns into positive infinity over here. This negative right here was from the original fraction, which was already minus as it was. This negative infinity becomes positive infinity over here, but these go to 0, leaving us with 2. So we got a different value of the limit for this particular function. So this is at to the left. So the horizontal asymptote at y equals 2 to the left. If we do it to the right, we're going to get the same result. Again, if you want to practice that, go ahead and do that. So the limit as x approaches positive infinity is also 2. So let's, in this case, we're going to do the same thing for example 4. We're going to raise this to the third power and see what happens to the function, to the limit. Okay, so let's look at an example 4. So here we are changing this power and upping it by 1. So now it's 2x to the third power. So what happens to the end behavior of this function on the left side as x approaches negative infinity? So again, if we do a direct substitution and substitute negative infinity in for x, notice that as we plug this in, okay, so I went ahead and corrected a typo on here. I put here to the second power, should be to the third. So if we do a direct substitution here, if I plug in negative infinity in for x, we'll notice that you're going to get negative infinity to the third power. So if we show this, we get 2. Here, let me show you over here. So we get 2 times negative infinity raised to the third power. Now, negative infinity to a negative number raised to the third power is negative infinity. So this is why we get negative infinity on the numerator. Okay. So in any case, because we get an indeterminate form, we need to divide by the highest power of the denominator, which is x squared. So this is where we're going to do divide by x squared yet again. And then notice it cancels out here, leaving us with 1. Some of it cancels out with the 2x cubed, so leaving us with 1x left over. And so we get a similar expression, but here we got an x in front, with the 2x. In the previous example, it was just 2, but now we have 2x there. As we plug in negative infinity into that limit, you're going to see that, well, 2 times negative infinity is negative infinity. 2 times a negative number is negative. Negative number squared is positive, so we just got this positive infinity on the denominator. Same thing for here. But we know that these turn to 0, but a negative infinity minus 0 is negative infinity. So we're left with negative infinity. This is an infinite limit. This is an infinite limit at infinity. This is what we call it. If we got a limit at infinity and we get infinity for the limit, then this is an infinite limit at infinity. So it's combining those two. But in any case, if you got infinity for the limit, then that you can also replace that with does not exist, because an infinite limit does not exist because it doesn't approach a number. So by definition, it does not exist. All right. So note that in this case, there is no horizontal asymptote to the left because decreases without bound. So there's no value that it approaches. And we're going to see that in this example, even though there's no horizontal asymptote, that doesn't mean that it's not actually approaching a line. It's blowing up to infinity, of course, in the negative, but there's still an asymptote here, but it's called a slant asymptote. We'll look at that in just a second. So if we do the limit at infinity, we're going to get positive infinity rather than negative infinity. But in any case, there's still no horizontal asymptote. All right, so I'll note on example 4. So as I mentioned earlier, this actually has an asymptote, but it doesn't have a horizontal asymptote. It has what we call an oblique or slant asymptote. So another way to do this example is to use good old polynomial long division. So if you remember polynomial long division, well, it's a very useful way to simplify rational expressions, right? If you don't remember, we're gonna run through the division process here. So again, the numerator is the dividend, the denominator is the divisor. So the denominator goes on the outside of the table here. All right, so we got our division table here. And notice that because we don't have any powers of x squared or x to the first power, we must include them in the dividend and divisor if we're missing any of them, because they serve as place value holders for if we get any second or first powers of x. Okay, so they're just simply there for place value holders. All right, so how many times does x squared go into 2x cubed? Well, we know that if we multiply x squared by 2x, we get 2x cubed. So 2x times x squared is 2x cubed. We're going to distribute this to this entire expression. So 2x times x squared is 2x cubed. 2x times 0x is 0x squared. And then 2x times 1 is 2x. Then we're going to subtract. Just like with division, we multiply, we figure out how many times it goes into it, multiply, and then subtract the result. So in this case, we get these cancel. We have 0 minus 2 is negative 2. Remember, we're subtracting here, so 0 minus 2 is negative 2. And then we got negative 1, just bring down the negative 1. How many times does x squared go in the negative 2x? Well, the answer is it does not, because you got x squared, and this is x to the first power. So therefore, this is our remainder, all right? So this is our remainder term. So what do we do with remainder terms? We put the remainder term over the divisor, okay? And this is our remainder term. Okay, so remember the form of a quotient is you got your quotient part plus your remainder divided by your divisor. Okay, that's the structure of it. If you have a remainder, then it's going to go in the numerator there. All right, so in this case we have our rational function in terms of a simplified form. In terms of it doesn't look that much simplified, but it actually is going to help us out with what we're going to do next. All right, so now we can plug in for the denominator, or for the fraction piece here, we're going to divide both the numerator and denominator of that by x squared, just like we normally would, right? In that case, these will cancel out, leaving us with 1, and then one of these x's cancel out, so we get negative 2 over x, right? So, the usual process here. Then we're going to plug in negative infinity in for x here, but we're going to do it just for the fractional part. We're not going to do it for the 2x part, because we're going to look at that in just a second. But notice that for the fractional piece, these go to 0 because you got infinity on the bottom, and you have this 1 here that stays. So everything else goes away. So in other words, this here, this is 0, this is 0, and we're left with 1. But 0 divided by 1 is 0. So this basically all goes away, leaving us with the 2x part. Now, this is why I didn't plug in infinity, but now we can plug it in. If we plug in negative infinity, we get the negative infinity that we got earlier. But this 2x is actually your slant asymptote. So this, even though there's no horizontal asymptote, there is a slant asymptote at this function, 2x. So remember, y equals 2x is a line with a slope of 2, right? That goes through the origin. So if we graph this function, we have the function in red, and then we have the slant asymptote at 2x. So this is the slant asymptote, SA, which is at y equals 2x. This is the line that goes to the origin with a slope of 2. So it is approaching something, but it's still blowing up to infinity, right? Or negative infinity, depending on which direction you're looking at. All right, so let's summarize what we just said about with those examples. So I selected those examples for a reason, noting that on some of the examples, the degree of the numerator changed, right? So the numerator had powers that changed. In the first example, the degree of the numerator was less than the degree of the denominator. And notice that we got a horizontal asymptote at y equals 0. So here's an example of that. Another example. So the degree of the numerator here is 3. The degree of the denominator is 4. Remember, the degree is the highest power of x. So here we got 4 for the denominator, 3 for the numerator. So we know that the degree here is less than there, and therefore we have to have a horizontal asymptote at y equals 0. So again, we're going to demonstrate this using calculus. So if we divide by the highest power of x for the denominator, that's x to the 4th power, we're going to divide everything by that. And so a lot of these cancel out, right? Leaving us with this simplified fraction. We got this 1 for x to the 4th cancels out, 2 of these cancel out, 1 of these cancel out, so on and so forth. But then if I plug in infinity, then we notice that anything that has x on the denominator with infinity is going to go to 0. Because a constant over infinity is 0. And we're left with 0 over 1, which is just 0. So we've shown that we have to have a horizontal asymptote y equals 0 if the degree is less for the numerator. Now, if we have the degrees equal to each other for the numerator and denominator, then the limit at infinity for that particular function, is the ratio of the leading coefficients of the numerator and denominators. So we're going to look at an example of this. So in this case, the degree of the numerator is 4. The highest power is 4. The degree of the denominator is 4. The highest power is 4. So then the limit must be the ratio of the leading coefficients. The leading coefficient here is the coefficient for the highest power of x. So this is 2. The coefficient for the denominator, the leading coefficient, is an invisible 1. So the ratio is 2 over 1 is 2. So the horizontal asymptote is y equals 2 here. And we're going to show this using calculus. So we're going to divide by the highest power of x, which is x to the 4th, the highest power on the denominator. But we're going to do it to both numerator and denominator. Notice that a lot of these cancel, leaving us with this simplified fraction here, complex fraction. But if you plug in infinity into here, anything that has x on the bottom, when we plug in infinity, goes to 0. So 0, 0, 0 for these, and then a lot of zeros on the bottom. So we're left with 2 over 1, which is 2. So we've shown that it's the ratio of the leading coefficients. So now let's look at the third guideline. If the degree of the numerator is greater than that of the denominator, then we have no limit. The limit does not exist. The limit goes to infinity or negative infinity. So in other words, the function does not have a horizontal asymptote. But as we saw, and this is a typo by the way, this should say asymptote, so that should be a T there. It does not have an asymptote. However, if the degree of the numerator is 1 greater than the denominator, so that is the degree of the numerator is equal to the degree of the denominator plus 1. So if it's a difference of 1, meaning the degree of the numerator is 3, the denominator is 2, for example, then we can see that there is no horizontal asymptote, but there will be a slant asymptote, as we've shown in the previous example when we did the long division. If the degree is way higher than just by a difference of 1, there will be no slant asymptote, right? It'll be something very, very odd. All right, so here we go. So here's an example of this. Here we've shown that this is 1, this degree is 5, this degree is 4. If it's a difference of 1, there is no, if it's greater than period, if it's greater period, then there is no horizontal asymptote. However, if it's greater by 1, we have what is called a slant asymptote, okay? So this falls under that special case where we have a slant asymptote. All right, so if we evaluate the limit at infinity, we're going to divide by the highest power of x on the bottom denominator, which is x to the 4th. So just doing the math, simplifying a little bit, and then plug it in infinity. Remember, anything with x on the denominator goes to 0. So we're left with this 2x over 1. But then if I plug in infinity into x, you get infinity for the entire limit. And as we mentioned earlier, this 2x right here is actually going to be your well, you can probably determine that will be your slant asymptote, but in order to determine the slant asymptote, you can just perform a polynomial division like we did before to kind of show that. But in any case, we've summarized the 3 cases for horizontal asymptotes or lack thereof. Let's make a note on some functions that have square root of x squared. So there will be situations where you're going to have a radicals in the function that involve square root of x squared or fourth root of x to the fourth, anything like that. So it must be noted that the square root of x squared is a special case because notice that x could be negative or positive here. If x is negative, then the square root of x squared should give us a negative quantity, right? So for example, if x is equal to negative 5, but we take the square root of negative 5 squared, right? Well, we note that if we square negative 5, that gives us a positive number, right? So we get the square root of positive 25. However, we know that the square root of 25 is 5. However, x was negative 5, so you should actually have negative for a quantity when you evaluate this, or you would think that you would get a negative quantity, right? So some students, what they would do is these would cancel out, and they get the result that it's equal to negative 5, right? So what we're saying is that some students end up canceling this out and get negative 5. But so we're going to put that as a question mark. So which one is correct? Is it negative 5 or 5? So in order to address this question, what we do is we define the square root of x squared as absolute value of x. So if we take the square root of x squared, we define it as not just x, but the absolute value of x. So this is strictly a positive quantity. So the answer to this question is that if x is positive or negative, we're going to, regardless of whether it's positive or negative, we're going to get a positive quantity for this. Because remember that you can't take the square root of a negative number, and the square root function only gives you positive quantities, right? The square root function can never give you negative quantities. This function right here, just in general, like the principal square root function gives you positive quantities. So the answer is it's going to be 5, not negative 5. So I'm going to cross this out. But if we define the square root of x squared as absolute value of x, then if x were negative 5, when I do this, I get negative 5 squared. Well, then this is going to be the absolute value of negative 5. And we know that the absolute value of negative 5 is 5. Okay, so we're going to define the square root of x squared as absolute value of x. So when x is negative or positive, we're still going to get a positive quantity per se. Okay, so let's look at this example. So if we have this example, we can see there's a square root of an x squared there quantity. So when we actually divide by x squared, or when we use this square root of x squared, when we involve it in the evaluation of the limit, we need to be able to deal with that situation. So, like I said earlier, in these situations, we're going to say that it's equal to absolute value of x. So, which means that it's equal to x when x is positive, but it's negative x when x is negative. So remember that the definition of absolute value x is that it's equal to x when x is positive, or 0, and it's equal to negative x when x is negative. So if I were to evaluate absolute value of negative 5, well, that's equal to, well, negative 5 is less than 0. So therefore, it's equal to negative x. But we know that x is negative 5. So it's going to be negative x, which is positive 5. So we end up getting the same number, a positive number, okay, using this definition here, right? So if we use that definition, then in general, this works not just for square root of x squared. This works for any index where the index and the power matches, but only when n is even. Okay, so for example, this works when we have square root of x squared. This works when we have fourth root of x to the fourth. If we have sixth root of x to the sixth, these are all equal to absolute value of x. Okay, So anytime we see an odd or an even index with the same power of x, we're going to call it absolute value of x, all right? So at the end of the day, if it's odd, we're just going to call it x. We're not going to call it negative absolute value of x, okay? And the reason being is that, remember that the cube root can be negative. So if we got, for example, the cube root of -8, well, that's just -2. You can get a negative number from a cube root, a fifth root, a seventh root, an odd root, but you cannot get a negative from an even root. So that's really what it boils down to. Okay, so if we look at our example, the example that we provided, well, we have to divide by the highest power of x in the denominator. But the highest power of x in the denominator is x squared. In fact, it's the square root of x squared, because if we divide this by x squared, it's all under the square root. And therefore, when we divide by x squared, we're really dividing by square root of x squared. Okay? So in other words, if I take this denominator and I divide by x squared, well, I'm actually dividing inside the square root, right? So this is all inside the square root. So I'm actually dividing by square root of x squared, okay? So this is why in this example, we just write it out separately as square root of x squared, okay? So we're dividing by that, but if we divide it on the bottom, we have to do it on the top, okay? So if we do this here, we're gonna do it on the numerator and denominator. So we're gonna split this up and we're gonna divide the denominator by this x squared, right? The square root of x squared. But when it goes in, this cancels. So these cancel, one of these cancels, and so on and so forth. And we get this simplified denominator. On the numerator, however, remember that we said that the square root of x squared is absolute value of x, right? As we mentioned over here. In this bullet point, right here, sorry. So because it's the absolute value of x, that changes things, okay? That's going to change the absolute value of x rather than just x. So this is how you use this definition in an example. Okay, so this is going to be very important as we do the next example. So if we continue this, then we say that, okay, well, when absolute value of x when x is positive, this absolute value of x turns into x, right? So it doesn't really do anything to the function, it just changes it to x. And then we know that these x's cancel, leaving us with 5 minus 1 over x. We just distributed the x here and here. However, notice what happens if x is negative. If x is negative, then this absolute value of x turns into negative x. So let me get rid of this here. This absolute value of x turns into negative x. So see the change here from here to here, right? Using the definition of absolute value right over here, right? So that changes the limit or the value of the function. So now this negative goes on the outside. So this is negative, whereas here this was positive. So notice the change. So when we do the limits are actually going to change. It's going to make a difference whether we do negative infinity or positive infinity. Okay, we're going to expound on this in just a second as we look at an example. But before we look at another example, let's notice what happens if we have square root of x to the fourth. So far I said that this works for fourth root of x to the fourth, square root of x to the second, as long as the power is even. However, what happens if we have square root of x to the fourth? Well, if we break this down into x squared times x squared, we notice that both of these turn into absolute values, right? Well, the absolute value of x times the absolute value of x is absolute value of x squared, which this is always going to give you a positive quantity no matter what, so we can just leave it as x squared. So there's no need to include absolute values for square root of x to the fourth. All right, so let's look at another example of that. So if we had an example like x to the sixth, well, now it does matter because we know that we need 3x squareds to get x to the sixth power, right? X to the second, x to the second, x to the second. If you add those exponents, you get 6. Well, each of these turned into absolute value. But we noticed that when we had 3 absolute values, now we get x to the third power. Now, x to the third power can be a negative quantity. And so it does matter that we include the absolute value because we want this quantity to be strictly positive. And so it has to be absolute value. Okay. Whereas here, it's going to be positive anyway, so it doesn't really matter. You don't have to include the absolute value. Whereas here, it could be potentially negative. So we want to avoid that. All right, so something to keep in mind. If we have fourth root of x to the 8th power, well, we know that this is x to the 4th times x to the 4th, but then with the fourth root, of course. We notice that these turn into absolute values. So here, you don't have to put the absolute value because it's x to the 2nd power. Here's one more example. If we have fourth root of x squared, or x to the 12th power, there's 3 of them, and in this case, it does matter. Okay, so as long as this power is odd, it does matter that you include the absolute value. If it's even, it doesn't matter. All right, so let's apply what we just said to the following function. So we're going to do the horizontal asymptote to the left and to the right. So this one, the horizontal asymptotes will change when you do positive infinity versus negative infinity. So let's see what happens. So let's do the limit at negative infinity. So remember that if we're going to divide by the highest power of the denominator, the highest power of the denominator is square root of x squared. All right, so because it's x squared, but it's under the square root, right? So this x squared is underneath the square root. So we need to divide by the square root of x squared. So we're going to do that. We're going to do that to the numerator and denominator, noting that this turns into absolute value of x, right? And this, we're going to divide into the denominator, okay? So we're going to divide that into the denominator because they both involve square roots, so we can put them under one common square root. Whereas this does not have a square root on the numerator here. So we're going to leave it as absolute value of x by definition here. All right, and then we're going to just cancel these x squareds on the denominator. All right, we're going to cancel in just a second. I forgot to cancel it here, but let me just say that they're canceled. Now here, this turns into negative x because now we're using the definition. Since we're doing the limit at negative infinity, that means x is less than 0, right? X is negative. So we have to apply the definition. Since x is negative, this turns into negative x, okay? All right, so in that case, if we distribute this here and here, we get that this over negative x, these cancel, but this becomes negative 3. And then this becomes positive because you have the double negative situation there. And then, of course, these canceled out, so leaving us with 2. Then we're going to plug in the infinity limit there. If we plug in negative infinity into here, well, that becomes positive infinity because it's squared. But then 1 over infinity is 0. This goes away. And then this goes away as well. So leaving us with negative 3 over square root of 2. So there is our limit. So now we know the horizontal asymptote to the left is negative 3 over 2. Now let's look at the horizontal asymptote to the right. So if we do the same process, divide by square root of x squared on the numerator and denominator, this time, we notice that this turns into absolute value, x, but since x is positive infinity, that means x is greater than or equal to 0, which means that the absolute value of x turns into positive x, just regular x. So everything else is the same except for that negative x part. So notice that it's just going to cancel out here. And then if we plug in the infinite limit, we get positive 3 over square root of 2 instead of negative because we no longer have the negative from the absolute value. Therefore, the horizontal asymptote to the right is positive 3 over square root of 2. All right, so this is an example where the horizontal asymptote to the left and to the right actually varies. Let's show you, we'll go ahead and look at so essentially if you were to graph this, you would get the case where you have let's pretend that we know how this function looks like, but 3 divided by square root of 2 is, approximately 2 or so. Let's just say that this is 3 over square root of 2, and this is negative 3 over square root of 2. So the function kind of, this is just an approximation. As x approaches positive infinity, we note that the function is approaching this asymptote right here, but as it approaches negative infinity, this is a negative infinity here, the function is approaching this asymptote right here on the left side. So it kind of looks like that. So on the right side is approaching one asymptote, on the left side is approaching a different one. Okay, this is not exactly how the graph looks like. This is just an example to kind of demonstrate. All right, so let's look at an example where we have infinity limits at infinity. So these are limits at infinity that gives us infinity or negative infinity. All right, I know it's a mouthful, infinity limits at infinity. But if we look at the question here, if this is just 5x to the third power, so just do a direct substitution. That's just a polynomial. We know that a polynomial raised to x raised to the third power, hopefully you know that. If not, just you can go back and review. But since this is a cubic function tends to look like this, right? So you tend to have behavior where it goes down here and then up on the right side. Well, that means as x approaches negative infinity, as x goes more and more negative, which means you're approaching that side of the axis, well then the function's going down to negative infinity, right? So we're going to get negative infinity for this, naturally. And that makes sense. If you plug a negative infinity into there, well, a negative number to the third power is negative. So this turns into negative infinity, or does not exist. Hence the infinity limit. If you do the second part, well, we notice that remember that the function for sine starts at 0, and then it has this wave, right, oscillatory behavior. So as x approaches positive infinity, as x gets bigger and bigger, the function starts, oscillating up and down, up and down, up and down. And so it doesn't approach a single value. So therefore, it's not technically infinity. So this is not an infinity limit right here. This is not infinity limit. So this is an infinity limit at infinity. This is not an infinity limit in the usual sense, right? It's just it's a limit where it oscillates. It doesn't approach a single value. But in any case, it does not exist. This is why I don't put infinity. It just does not exist. So for C, however, if I do this is, you're going to actually get a value here, and we're going to show you why you get a value for this guy, okay? So if I look at, we notice that sine x is between negative 1 and 1. So if I draw the traditional sine function, it goes between 1. It actually starts here. So let's draw it out here. So this is our x and y axis. It starts at 0 and it goes up to 1 and it goes down to negative 1 eventually, and it bounces between 1 and negative 1. So this is by definition, if you look at the graph, we know that it's between negative 1 and 1. And then if we divide all three sides by x so that we can get the same form here, then notice that if I take the limit as x approaches negative infinity, this is going to go to 0 and this is going to go to 0. So that means that the limit has to be between 0 and 0. But we know if that's the case, it's got to be 0. This is by the squeeze theorem. So we've essentially shown that the limit at infinity of this is actually 0. So this is not an infinity limit. It's a limit at infinity, but it's not an infinity limit. The only infinity limit here is actually a, right? So we actually get a value here, interestingly enough. All right, that is it for the lesson, guys. So now we are just looking at review. So we're reviewing the concepts. So my suggestion is pause the video and see if you can answer these questions. You're matching the graph to the function by essentially doing a limit at infinity for each of these. All right, so here's the first part. If you want to pause, the second part is here. This is part 2. We're going to go through all these questions. Again, if you want to go through a specific question, the rest of them are easy. You can just easily skip through the part that you need help with. But here are some problems. All right, so we're going to go ahead and take a look at solution, or this, the solutions for these exercises, starting with number 1, of course. So if we look at number 1, remember we are trying to match it to the graph. So we need to, in order to do the horizontal asymptote, we need to establish what's the limit at infinity, right? So we're going to do the limit as x approaches infinity, and we got to do it for negative infinity as well. If it's obvious it's going to be the same, we'll say that it is. All right, so here we're going to do the limit as x approaches infinity of the function. So here's the key. If you don't have any square root of x squareds or any absolute value of x's or anything like that, this means that most of the time the limit on both positive and negative infinity are going to be the same. So here, both sides are going to be the same. We don't have to worry about it because we don't have any situations with absolute value or anything like that. So in this case, divide by the highest power in the numerator and denominator, which is x squared. So we're going to divide everything by x squared. So we got the limit as x approaches infinity of 2x squared divided by x squared. And then we got x squared divided by x squared plus 2 divided by x squared. Well, these cancel, leaving you with 1. These cancel, leaving you with 2. So we got that we get the limit as x approaches infinity of 2 over 1 plus. Now if we plug an infinity into here, this turns into 0 because a constant over infinity is 0. So we get that the limit is 2. And again, this is going to be the same thing as the limit as x approaches negative infinity. It's not going to change just because it's negative infinity. So it's actually the same on both sides, okay? Because we don't have any funny business going on with the square root x squared, that stuff. All right, so in this case, we're going to match it, so the limit has to be 2. If you remember the guidelines, you know that the powers are the same, so therefore the limit should be 2 over 1, right? So you can shortcut this and do that if you want. However, I do suggest practicing the idea of the infinite limits, right? Limits at infinity. Practice this concept because eventually you might need it, right? For something, different. All right, so here we go. So which one has a horizontal asymptote? So we have a horizontal asymptote at y equals 2. All right, which one has a horizontal asymptote at y equals 2? Well, it looks like it's got to be f, right? That has a horizontal asymptote at a value of 2. There's another one that does. Actually, there is another one that does, now that I think about it. This one has a horizontal asymptote of 2 right there, right? So which one is it, right? Is it A or is it F? Well, okay, let's look at the y-intercept. We notice that the y-intercept here is 2 because that's where it crosses the y-axis. The y-intercept here is 0, so does it start at the origin? The answer is it does start at the origin. If we plug in 0 into the function, so if we plug in 0 into this function, we get 0, right? So f of 0 is 2 times 0 squared over 0 squared plus 2. Which is 0. So it does actually start at 0, so that indicates it's got to be this function right here, okay, and not A. All right. Actually, we also have another, and now that I think about it, we also have another function here that goes through 2, so we want to actually eliminate that as well. But again, as we established, it starts at the origin, and E does not start at the origin, so it cannot be E. So we eliminated that as well. So the answer has to be F. Okay, so let's look at another example. This one has the square root of x squared business, right? So that means that we're going to have 2 different limits, right, from the right and from the left. So we have to be able to establish the 2 different ones. All right, so in this case, the highest power of the denominator is square root of x squared, right? So we're going to divide everything by square root of x squared. So let's do that. So we get the limit as x approaches infinity of 2x over square root of x squared over, and then we're going to just divide this inside, okay? So we're just going to divide it inside, because if we can bring the square root of x squared into the square root here. So we got 2 over x squared. All right, so these cancel, leaving us with 1. So we got on the denominator, let me do this over here. So we get limit as x approaches infinity. And we get square root of 1 plus 2 over x squared. Now remember that this is going to turn into absolute value of x. And because this turns into absolute value of x, because we're dealing with positive infinity here, that means x is greater than 0. So this is actually going to turn into x. So actually it just becomes x. We don't even have to worry about the negative x portion for positive infinity, okay? So this is going to turn into x. All right, now I want to note that we can also establish a parallel. So if we do the limit as x approaches negative infinity, well, this is now going to turn into negative x. So I'm going to go ahead and skip straight to that. So if we do negative infinity, this is going to turn to negative x, right? Because the absolute value x is going to turn into negative x. So this will establish a parallel between the two, so you can kind of see them at work. All right, so here this becomes 2, whereas this becomes negative 2. So we got 2 here, but negative 2 here. If I plug in infinity into this, this goes to 0. So now we have square root of 1, which is just 1. So we got 2 over 1. This is going to be the same thing. This is going to be negative 2 over 1, but negative 2. So you can see that the limit, the horizontal asymptote on the right side is 2, on the left side is negative 2. So which one has that? Well, this one is 2, this one's negative 2 for the asymptotes. So it makes sense that it'll be something like that. There's nothing else with 2 different horizontal asymptotes like that. So this has to match up with C. Okay, so let's look at yet another example. So we're going to be matching these. Now this one doesn't have any square root of x squared, so it only has one horizontal asymptote on either end, on both left and right. So let's just do the positive infinity. We're going to divide by the highest power, which is x squared. Keep in mind that the numerator is less than the denominator, the degree, so we should get a horizontal asymptote at 0. Again, using the shortcut, but we're going to demonstrate this using the calculus. So divide numerator and denominator by the highest power. All right, so x squareds cancel. This is 1 over x. Now if I plug in infinity into the denominators, this goes to 0, this goes to 0, leaving us with 0 divided by 1, which is 0. So we got a horizontal asymptote of 0. So, so which one has a horizontal asymptote of 0? Well, if you notice, if you look at the function, so if you look at the function, this appears to have a horizontal asymptote at 0. So if you see that, it seems if this is approaching 0 there, and then as x approaches negative infinity, it's also approaching 0. So in other words, it's approaching the x-axis, and the x-axis is 0, right? Y equals 0. So this looks to be D. And we can also establish that this is actually a this function is symmetric about the origin because it's odd. Remember that odd functions, such as this is an odd function. Because if I plug in negative for x, this turns the whole fraction, the whole number completely negative. Odd functions are symmetric about the origin. So it really does actually look like D if you take a look at it. All right, so number 4. Here we have, okay, so this one's interesting. This one's kind of already done with, I guess they must have done a polynomial division of some sort. But if I take the limit as x approaches infinity of that function, well, we're going to divide by x to the 4th. Or, well, actually, yeah, we're going to divide by x to the 4th, top and bottom. So then this cancels, becomes 1. This becomes 2 of these cancel, so this becomes x squared. So we're left with limit as x approaches infinity of 2 plus 1 over x squared over 1 plus 1 over x to the 4th. So if I plug in infinity into here, this goes away. Here, this goes away, becomes 0. So we got 2 plus 0, which is just 2. So we got the limit. The horizontal asymptote is 2 as x approaches positive or negative infinity. Now, also notice, that if we look at the y-intercept, so what happens if x is 0? If we plug in x is 0 into this function, we get, well, this becomes 0, so we get 2. So we got a coordinate at 0, 2. So if you look at these, which of these have a coordinate of 0, 2? The only one that has a coordinate of 0, 2 is this guy right here. So that has a coordinate of 0, 2, and it has a horizontal asymptote where it approaches this value of 2, right, on either end. So the answer has to be A for number 4. Okay, so for number 5, we got basically a couple more to go, a couple more graphs to match this up to. So if we do the limit as x approaches infinity, there's no square root of x squareds or anything like that, so we're okay when it comes to that. We're going to divide top and bottom by x squared. So we got 4 sine x over x squared And then if I divide this by x squared, this is going to be 1 plus 1 over x squared. So I went ahead and just skipped the step there, but just dividing the denominator by x squared. Okay. All right, so notice that if I plug an infinity into here, this goes away, this goes to 0. Now for the denominator part, it's useful to write this in the form, so before I call this, we know that that's going to go away, but let me just rewrite the limit here, and I'm going to rewrite the numerator part as sine of x over x, and then 1 over x, okay? So we're going to do that for a reason. So we know that this goes to 0 if I plug infinity. We know that this goes to 0 when I plug an infinity there, because 1 over infinity is infinity. And we established in an earlier example that this is actually going to go to 0. Remember, we established by the squeeze theorem that this is actually between 0, the limit of this as x approaches infinity is between 0 and 0. So this actually goes to 0 by the squeeze theorem. So we end up having 4 times 0 times 0, which is just 4. Which is just 0, sorry. So we get 0 in the numerator. So 0 over 1 plus 0 is 0. So we got a horizontal asymptote at y equals 0. And we already established that this was one of the earlier questions. Now, another thing to note is that we're going to find an x-intercept for this. If I plug in 0 for x, we're going to get 0, right? So this actually goes to the origin because sine of 0 is 0. Now, we also note that sine of pi is 0 as well, right? So that's an x-intercept. So if I plug in pi for x, which is 3.14, I get 0. So we also have an x-intercept at pi comma 0. So we're going to see a function that has that. So if I look at this one looks like it's approaching 0 here and here, right? Or it's eventually going to be approaching it. But it also has a x-intercept at 0, and it has an x-intercept at right over here, which guess what that is? That's 3.14. That's pi, right? And it has another x-intercept here at negative 3.14 at negative pi, essentially. So that's why it's crossing here at pi. So remember that a function can cross the horizontal asymptote, but it still should eventually approach it, right? So even if it crosses it, it doesn't mean that it's not a horizontal asymptote. It could still cross a horizontal asymptote as it does here. It actually crosses here, but then it still approaches it at infinity, ultimately. All right, so that takes care of that one. So if we look at number 6, this one, the one that we didn't match up to goes to this one, obviously, but let's go ahead and just, practice it anyways. We're going to cheat and use the shortcut here because we've already shown you how to do limits at infinity. So we note that the degree of the numerator is 2. The degree of the denominator is also 2. So therefore, we can take the ratio of the leading coefficients. That's 2 and then visible 1. So we got a horizontal asymptote at 2 over 1. That makes it so much easier, I know. But again, we showed you how to do it with the infinite limits. So we're just going to take a shortcut for this guy. So it has a horizontal asymptote at 2. And in addition, if we plug in 0, if we plug in f of 0, let's plug in 0 in here, you get a y-intercept of 5. So we're looking for a function with a y-intercept of 5, which looks like this one, and it has a horizontal asymptote at 2 from the left and from the right. So it looks like it's e. And then we know that that's got to be e because that's the one that's left over. All right, that takes care of part 1 of the review. So now we're going to look at the part 2. So the last few questions here, which involve infinite limits. Okay, so for number 7, keep in mind that we're going to divide by the highest power of the denominator in this example. So keep in mind, if you wanted to cheat and use the shortcut, then you would get that, well, the degree of the numerator is 3 over 2. The degree of the denominator is 5 over 2. So the limit at infinity should be 0, right? The horizontal asymptote should be 0. So we should get a value of 0. Again, if you want to practice, go ahead and do the limits, right? So we're going to go ahead and do that. We're just going to show you the work here. So we're going to divide by x to the 5 halves for top and the bottom as well, okay? So we'll divide this by x to the 5 halves as well. Sorry, this would be a division sign there. All right, so we got x to the 3 halves over 5 halves. So remember, 3 minus 5 halves is 2 halves. So, okay, so if I do 3 halves and then x to the 5 halves, well, I just subtract those exponents. So 5 over 2 minus 3 over 2 is 2 over 2, right? Which is just 1. So what this is saying is that I'm going to get square root of, well, what this is saying is that I get x to the second, 2 over 2. So this is the same thing as square root of x squared. So just be careful with this. You're going to get square root of x squared when you do this. So x to the 2 over 2. And we just established that x to the 2 over 2 is equal to absolute value of x, right? But here, because we're doing a limit at infinity, it's just going to be x. So it doesn't really change anything. So just a side note. So in this case, we get absolute value of x, which is just x. So we get x plus 2 over x to the 5 halves. All right, over, and then we get 1 minus 1 over x to the 5 halves. Now if I plug an infinity into here, this goes away, this goes away. Oh, I wrote x over here. This should say 1 over x. I apologize. So this is 1 over x because the highest power is in the denominator. So this becomes 1 over x. 1 over absolute value of x, which is just 1 over x. So yeah, 1 over x, I apologize. So if I plug infinity here, this is going to go to 0. So we get 0 over 1, which is 0. As we mentioned, we knew it was going to be 0 because the degree of the numerator was smaller. All right, for this one, find the limits. Same way, so let's go ahead and divide. We're going to divide by x to the 3 halves power, top and bottom. All right, so we got limit as x approaches infinity. We get 5 over x to the 3 halves. Keep in mind that x to the 3 halves is the same thing as x to the 1 half times x to the 2 halves. And we know that x to the 2 halves is absolute value of x. And then this is just square root of x to the 1 half is square root of x. So this is absolute value of x times square root of x. But again, since x is approaching positive infinity, that's not going to really change this. It's just going to be x, right? So it's going to be x times square root of x, which is just x to the 3 halves. So it's not really going to do anything to this problem. But I just want you to keep in mind that these things do exist, and you just want to be mindful of them if they do make a difference, which it doesn't in this case. So we get minus, and then these cancel. So we get 2, which we just get 2 in this case. Again, note that the degree of the numerator is 3 halves. The degree of the denominator is 3. So really the answer should be negative 2 over 3 if you wanted to shortcut it. But let's find out what it is. These cancel, leaving you with 3. You get 1 over x to the 3 halves. If I plug in infinity here, this goes away. If I plug in infinity here, that goes away, leaving me with what I just told you, negative 2 over 3. All right, so notice that the degree of the numerator is larger than the degree of the denominator. So we should expect that the limit is going to go to, infinity or something like that, infinity or negative infinity, whatever. It's not going to exist because this is 3 halves. The degree for that is 1 half, because remember, square root of x is the same thing as x to the 1 half power. So yeah, 3 halves is bigger than 1 half. So we should get does not exist here. But we're going to show our work. So let's divide everything by, this is the same thing as x to the 1 half power. So I'm just going to write it as such, okay? So I'm going to divide by x to the 1 half power. Again, practice your rational exponents if you need a refresher on that. So we get 5x to the 3 halves divided by x to the 1 half, which is 3 halves minus 1 half, which is 2 halves. So it becomes, so x to the 3 halves minus 1 half is x to the 2 halves, which we said that is absolute value of x. But here it's just going to turn to x because we're doing positive infinity for the limit. All right, so we get 5x over, and then so these cancel, so leaving you with 4, and then you have 1 over x to the 1 half power. If you plug in infinity here, this goes to 0, but if you plug in infinity here, you get infinity, because 5 times infinity is infinity, right? So you get infinity divided by 4, which is infinity. So the limit is infinity, or does not exist. All right, so looking at number 10, if we plug in negative infinity to this one has a square root of x squared, so it might make a difference here. So we're gonna excuse me, we're gonna divide by the highest power of the denominator. The highest power is x, right, for the denominator. So we're gonna divide numerator and denominator by x. All right, but keep in mind that if we divide the denominator by x, right? So let me just write this out. So we're going to divide this by x, so this goes away. So I'm just going to divide both of these by x. So it's going to be 2 minus 1 over x for the denominator. Now for the numerator, what we get is we're actually dividing this by square root of x squared. And the reason is because if we plug it into the numerator and we actually divide it in, then that's when we get, then x is going to turn into x squared, right? If we bring this x, so if I write this out, if I bring this x inside to divide, well then it's got to go inside the square root, right? So if it goes inside the square root, it has to turn into x squared, because now, you know, x squared and square root cancel out, leaving us with x, right? So when we're dividing, we're actually doing this, right? So essentially, dividing by x is the same thing as dividing by square root of x squared, okay? But we have to keep in mind that the square root of x squared has to be a positive quantity. So when we do the limit as x approaches negative infinity, it's going to make the this turn into absolute value of x, okay? So so this is actually going to turn into absolute value of x, is what I'm trying to say. But we know that as we excuse me here. Okay, so for this, real quick, I want to elaborate. So for this square root of x part, so I'm going to backtrack a little bit here, and I'm going to just leave this as square root of x. I'm going to leave this as square root of x squared. So let me go backtrack here, because for this part, okay? So essentially we're dividing by x, right? But we're dividing by square root of x squared, right? So really what I should be saying is that this is the same thing as square root of x squared, right? Because if I divide this by square root of x squared, then that means I'm dividing this by square root of x squared. I'm dividing by the same thing top and bottom. So I can't just do, like, for example, square root of x squared here and then just call this x, right? I got to do the same exact thing. So in other words, I'm dividing by square root of x squared. Top and bottom, so they got to be the same. Now for here, it doesn't matter, I can just divide into it and that's not going to change anything. So let's just go ahead and divide that into it, and we get this, right? We get exactly what we'd expect, you know, divide those, cancel those out, and we get just square root of 1 minus 1 over x squared. So that's the part that I went a little bit too ahead on that. Now for the denominator, we know that square root of x squared is absolute value of x, right? Absolute value of x. So that's actually going to change things. So because we're doing the limit as x approaches negative infinity, that means x is less than 0, which means that absolute value of x turns into negative x, right? Just as a side note. So this is actually going to turn into negative x. So we got 2x minus over negative x on, so we're going to divide both of them by negative x, essentially, is what I'm saying. Okay, so when I do that, this turns into negative 2, and this turns into positive 1 over x. Right, and that's what we're talking about. And of course, we got to do the limit as x approaches positive infinity, which I forgot to write, but there it is. Then if we plug in infinity, this goes to 0, and this goes to 0. And so we're left with square root of 1 over negative 2, which is negative 1/2. There you go. So as x approaches negative infinity, this becomes negative 1/2. If I were to do the limit as x approaches positive infinity of this function, I'm just going to call the function f of x, then we get positive 1/2, all right? And so what that indicates is that this graph is going to look kind of like this, where the right side approaches positive 1/2 and the left side approaches negative 1/2, okay? So that's sort of like how the function looks like, just as a, two different asymptotes on either side. So the answer is going to be negative 1/2 for this limit. So this one's an interesting one, which is why I wanted to provide it. So number 11, again, let's do the limit as x approaches infinity. So if we plug in infinity into this, okay, so for this one, we are going to apply a sort of squeeze theorem for this. We know that there's a couple ways to think about it. If you plug in infinity into this function, we know that this, or here, this is going to turn into infinity, right? So 1 over infinity plus sine of x. But then if we plug in infinity here, we know that this oscillates between -1 and 1, right? So really, the smallest that it can get is -1, the largest is 1. And so infinity plus that number, which oscillates, should take us to infinity. So we have 1 over infinity, which means we're going to get a value of 0, if you think about it, right? So if you think about the behavior of the functions, it makes sense that it's going to eventually go to 0. But we're going to show this with squeeze theorem real quick, just to kind of mention that. So again, we know that sine of x is between -1 and 1, right? The graph. So if we consider this function as a whole, well, then we know that this function has to be between, as long as x is positive, we're going to assume x is greater than or equal to 0. Or actually, x cannot be 0 here. So we're going to say x is strictly greater than 0. X can't be 0 here because that's a, that's 1 over 0, which is undefined. So as long as x is positive, then this function has to be between 1 over 2x plus 1 and 1 over 2x minus 1. Okay? And if you think about it, that's because sine of x is between 1 and -1. Now, if sine of x is -1 at its smallest, well, then that's going to make the fraction bigger, right? A smaller denominator means a bigger fraction. And if sine is 1 at its largest, then that's going to make the denominator larger, which is going to make the fraction smaller. So we're going to say essentially that this is between those two functions, right? Okay, so just kind of using that logic there. And then if we take the limit as x approaches infinity of every single side here, of course I'm running out of room, so I'm just going to write it small. So as we take the limit as x approaches infinity, we know that this term goes to 0, and this goes to 0. And so this shows that, okay, well, this limit here is squeezed between 0 and 0. And so by the squeeze theorem, then we know that this limit has to be 0. So therefore, this is equal to 0 by the squeeze theorem. Okay? So that kind of makes sense if you think about it that way. All right, so for this one, again, we're going to do the same kind of deal. Now, if you think about it, you can shortcut it and say that this is the same thing as x squared. This is the same thing, well, that's x to the third. The degree of the numerator is less than the denominator, so this limit should be 0. But we're going to go ahead and show you this real quick. So we're going to divide the numerator and denominator by the highest power of the denominator, which the highest power of the denominator is x to the third. So really what we're doing is we're essentially dividing by the square root of x to the 6, because the square root of x to the 6 is x to the third. So that's essentially what we're doing. And just to keep things consistent, that's why I keep them the same, right? Square root of x to the 6. But we know that square root of x to the 6 is the same thing as the square root of x squared 3 times, right, essentially. And so that's equal to the absolute value of x to the third power, which means that we do have to make sure that we include the absolute value there. Thankfully, it doesn't really do anything to the limit because we're going to see that we're going to get 0 anyways, but just to be on the safe side, technically speaking, this is an absolute value, so we're going to go ahead and include that just to be on the safe side. So we got, so here, if we do this, this becomes, well, we're just going to divide this into here. So if we divide it, we get x to the fourth over x to the third minus, x to the 6, not x to the third, I'm sorry. X to the 6, and then this is 1 over x to the 6. When we bring x to the third inside the square root, it becomes x to the 6th power. And then we said that this is absolute value of x cubed, right? So we can write this, yeah. But we know that because we're doing x is less than 0, this actually turns into negative x cubed in this example. Okay, so then that becomes negative x cubed as long as we got negative infinity. So in this case, we get x cubed minus 1 over negative x cubed, negative x cubed. So in this case, we get limit as x approaches negative infinity. This becomes square root of 1 over x squared minus 1 over x to the 6th power over negative 1 plus 1 over x cubed. But again, it doesn't matter because if I plug in negative infinity here, this goes to 0, and these both go to 0. So really, you're just dealing with 0 on the numerator. So we get 0 over negative 1, which is 0. So the limit is 0. However, in the case that it's not 0, you want to make sure that you're careful with the negatives and things like that, of that nature. All right, so on number 13, this one actually has an explicit absolute value. So remember that absolute value is equal to negative x when x is less than 0. All right, so in this case, this is going to turn into negative x. So we're going to do the limit as x approaches negative infinity of negative x over x plus 1. And so we're going to divide both sides, numerator and denominator, by x. So then these cancel out, leaving us just 1 and negative 1, right? So we get limit as x approaches negative infinity of negative 1 over 1 plus 1 over x. Then if we plug in infinity here, this turns into 0. So it leaves us with negative 1 for the limit. All right, so that takes care of that. So now let's look at the last question. So again, another absolute value. So again, so let's go over what the absolute value refers to. Remember that the absolute value of x is equal to, so this is the definition. It's x when x is greater than or equal to 0. It's negative x when x is less than 0. But when we're looking at a function like this is actually equal to itself when itself is greater than or equal to 0. And it's equal to the opposite of itself when itself is less than 0. Okay, so if we look at that template, we can see why that's the case. We have to set the inside greater than or less than. So in other words, this is equal to 3x plus 2 as long as x is greater than or equal to negative 2/3, or it's equal to the opposite of itself when x is less than negative 2/3. So we're just solving this for x here. Basically, we're solving these inequalities for x. But in any case, as x goes to negative infinity, we are looking at this scenario when x is less than this guy. So we're going to be using the opposite. So in that case, we're going to say we're going to turn this into negative. The opposite of itself, rather. Sorry. All right, so if we go ahead and continue with the limit here. Oops, I didn't mean to zoom in so far. Okay, so if we continue, let's, oh, I forgot to write the limit here. So let me write the limit here. Limit as x approaches negative infinity. All right, so now we're going to divide the numerator and denominator by x. First, let's distribute this. So we're going to distribute that, and then we're going to divide by x, the highest power of the denominator. So take that, divide by x, and then we got this plus 2 is going to turn to negative 2 because we're going to distribute that negative. All right, so again, these cancel, these cancel. So then we know if I plug in infinity into there, and there, it's going to turn into 0. All right, so in other words, we get negative 3 minus 0 over 1 minus 0, which is negative 3. So the limit has to be negative 3. All right, guys, that's going to do it for the end of the video. I hope you learned something. I hope you found this video informative. And I know it's pretty long. We had a lot of questions that we did, but I hope you found it useful. And as usual, I'll see you in the next one.